This video gives the final set of determinant rules and properties. So the previous video introduced rules and shortcuts which allow much easier computation. And what we're going to do now is introduce the last two rules that we think will be in common usage. Reminder of the rules that we've done so far. If a matrix is upper or lower triangular, then the determinant is the product of the diagonal elements. If a matrix has an entirely zero row or column, the determinant is 0. If you scale any row by lambda, you scale the determinant by lambda. If you multiply a matrix by a scalar, you multiply the determinant by lambda to the n. If you add a multiple of any row to another row, it does not change the determinant, and same for columns. If two rows or two columns are equal, the determinant is 0, and indeed if the multiple of any row or column is equal to another row or column, the determinant is 0. So those are the rules we've already covered. So we've got two more to go. So first of all, if you interchange rows or columns, you change the sign of the determinant. Here's a simple example with a 2 by 2. You can see with A, we've got AC in the first column and BD in the second column. And you'll notice when we've gone to B, we've swapped the order of the columns. Now when we calculate the determinants, it's fairly clear that these determinants have the opposite sign. So swapping the columns has changed the sign of the determinant for a 2 by 2 matrix. And you'll get the same result if you swap the rows. You can check that yourself. What happens if I do the same with a 3 by 3 matrix? So here I'm going to swap column 2 and column 1. So you'll see column 1 from A has become column 2 for B, and column 2 for A has become column 1 for B. So I've swapped two of the columns. Now let's do the determinant definition, and we'll use row 3. So there's the determinant of A. You can see I do A31 times the corresponding cofactor minus A32 minus A33 and so on. So there's the definition of the determinant for A. And now I'm going to do the same definition for B. But you'll notice a subtle difference that now I start with A32 because that's the bottom left coefficient, and then I've got minus A31 and so on. Now what I've got to do is look at these two forms. What I'll do is I'll erase some of these red markings so they don't get in our way, because we want to compare these two expressions and see what it tells us. If I look at this expression here, you'll find it's identical to this expression here. So those two are identical, but what you'll also notice, there's a negative sign on this one. If I look at the A32 expression, there's an identical expression here, but what do you notice? There's a minus sign there. And if I look at these last two, you'll find there's a subtle difference there. They might look the same. You might say, oh, they've both got a plus, but look, this one has got A11, A22 as the principal diagonals, whereas the corresponding elements down here are in the off diagonals. And so clearly there shouldn't be an equals naught there. I have to apologise for that silly typo. Clearly what you can see is that the determinant of A is minus the determinant of B, because every term in those expressions has got the opposite sign. So the terms in determinant of A have got the opposite sign to the corresponding terms in the determinant of B. Now you can extend this to larger dimension matrices. I'm not going to bother, but what you will see is that wherever you have corresponding terms, they come with the opposite sign. So we won't do 4 by 4 and higher dimension examples because it's straightforward for you to establish this and you would start getting a bit bored. Some examples then. So if you look at A and B, you'll notice I've simply swapped columns 2 and 3. So that column's gone there and that column's gone there. So I've swapped two columns, and what do you notice about the corresponding determinants? They're the negative one of the other. Different example, what have I done here? I've swapped rows 2 and 3. So row 2 has become row 3, and row 3 has become row 2. And what do you notice about the corresponding determinants? They're the negative one of another. So, we've got an example here where we're saying, can you exploit this change of column to make the problems easier? And what I'm looking at here is there seems to be lots of zeros, but they're not necessarily in a tidy position. But what I know is that diagonal or triangular makes the determinant computations a lot easier. So if I can move these zeros and give myself a matrix which is upper or lower triangular, then I've got a nearly a much easier determinant calculation to do. So the first thing I'm going to do is move the 3 zeros. So what I'm going to do is I'll erase that bit so you can see. I'm going to take the second column and make it the first column, and I'm going to take the first column and make it the second column. So I've swapped those 2 columns and I've added a minus, because that's what happens when you change columns. The determinant becomes minus what it was before. Still not quite right, because I've still got 2 more zeros here. So now I'm going to try and move those 2 zeros. So you'll see now what I do is I take this column, the second column, and make it the third column, and make it the 7. So that gives me another minus sign because I've swapped 2 columns again. So now I've got a plus. And you'll see the resulting determinant is now looking much, much easier. It's equivalent to 2 times 3 times the determinant of 2 minus 12 minus 6 minus 9. So you'll see with a couple of simple column operations, just swapping columns, I've reduced a 4x4 determinant to a very simple computation. So the determinant of a product is the product of the determinants. Now you might not use this one a lot, but it's a very useful rule. So I'm not going to prove this one, but in summary it means this: if you want the determinant of AB, you can do the determinant of A multiplied by the determinant of B. Or similarly, if you want the determinant of ABC, you can do determinant A times determinant B times determinant C. And often you will find a determinant calculation is much easier and much more efficient than a matrix multiplication. So if you can avoid matrix multiplication, then why not? So here's an example. You see I've given you a matrix A and a matrix D, both quite messy. Rather than multiplying them out, I've said I happen to know determinant of A, I happen to know determinant of D, 3 and 42, and determinant of AD is 3 times 42. So I could have got that result by inspection. So a summary then. So these first 7 rules are the ones that we did in the previous 2 videos, and what we've added in this video is a rule that says if you interchange rows or columns, you change the sign of the determinant, and the determinant of a product is the product of the determinants. Now what we want to do next is basically look at judicious use of these rules or properties in order to make difficult determinant computations become simple ones. And this is a core skill. And not only if you're doing things on pen and paper, if you're writing computer code to do determinant computations, you still want to be efficient and you want to know how to exploit these properties to make the computation as simple as possible.